In this short video, we're going to work on a few examples of Hausdorff regular and normal spaces. If you want to support the channel, you can do so in different ways. You can make a small donation or become a member on Ko-fi. By becoming a member, you get access to exclusive content. If in addition to that content you want to get some mathematics merchandise, then you can join us on Patreon. By becoming a monthly subscriber, you will get also t-shirts, hoodies, mugs, and many more. But if you only want the merchandise, then you can buy the items you want individually in our store. So let's continue with the video. The typical example of Hausdorff regular and normal space is obviously the real line with the standard topology. But this is a very boring example, so let's see something more interesting. What happens, for example, with the K topology? Well, our K is Hausdorff. This is very easy to see because if we have 2 points, x and y, because the K topology was generated by open intervals and open intervals minus k, then we can always find 2 open intervals around x and y just as we did with the standard topology. So there's nothing complicated here. But now let's see that our K is not regular. Remember that regular meant that a space can separate between a point and a closed set. And when thinking about our K, you might think, yeah, but in general it does satisfy this. But there is just one point and one specific closed set that doesn't satisfy the regularity condition. So let's take 0 to be our element x, and the set that we're going to take as a closed set that doesn't contain 0 is going to be k. K is trivially a closed set, because remember that we actually define the open sets to be intervals minus k, that k cannot be open. So K is a closed set, and K does not contain 0. Because remember that K was the set formed by numbers of the form 1 over n, where n was a natural number. So it didn't contain 0. Well, let's see if we can separate this. I'm not going to get very technical, because you can do all the calculations yourself. But here we're taking x to be 0, and our closed set K is going to be, well, it starts at 1, then 1/2, and so on, 1/3, and I'm starting to approximate, so it's very close there to 0. And so if I want to find an open set that contains K, that open set is going to be an interval. And if I have to grab all these elements, then immediately with an open interval, I will be grabbing 0. So if we want to find an open interval that contains k, yes, I could take a countable union of open intervals that contain each element, and then for 0 I could think about an interval minus k. But these will all be formed by open intervals like this. And so the intersection of the neighborhood I chose for 0 as any open set minus k and these intervals has to be non-empty for some of these elements here very close to 0. And that is why it's not regular. So this is a great example because what it's showing us is that there exist Hausdorff spaces that are not regular. There is one thing that we didn't check, and that is, to see the space is regular, we have to see that singletons are closed. But this is very trivial for the K topology, so I'm not even going to do it. Now let's look at another example. What happens now when we consider the lower limit topology? Well, we will see that RL is normal. For this, we again have to check first that the singletons are closed, but this is trivial again for the lower limit topology, simply because The standard topology is a subset of both RL and RK, and we know that single zones are closed for the standard topology. To prove that's normal, we will take two closed sets A and B. To picture this somehow, because we're in the lower limit topology, I like thinking about closed sets, so as sets that are something like this. This is just a picture, it doesn't have to be necessarily true. Because A and B are closed, that means that here we have a certain space in between. So if I take some element in A, I can always think about this neighborhood of A. Remember that we're in the lower limit topology, so we can take this extreme to be closed and an open interval here. And I can choose many neighborhoods like this that don't intersect B, so I can get very close to this point without actually getting to B. And the same here. I will just stay with one here in the middle, and I can do the same for B. If I grab an element here, I can always consider this neighborhood such that it doesn't intersect our set A. Remember that our sets don't have to necessarily be like this. I'm just trying to draw something so that we can picture what's going on. And I can continue doing this for every element in A and any element in B. So let's call these sets UA for the elements in A and BB for the elements in B. So obviously all these sets UA will be disjoint of the sets BB for every A and every AB in A and B respectively. So if I continue doing this for each A in A, what I'll end up having is that A can be covered by the union over all its elements of these sets UA, and B will be covered by all the elements in B, B, B. And we said that all these sets were disjoint, so if we call this union U and this other union B, then we have a neighborhood of A and a neighborhood of B that are disjoint. And so we have that RL is normal, because given two closed sets disjoint, we were able to find two disjoint neighborhoods of each of them. Now because it's normal, then it's also going to be regular and Hausdorff. Now a particularity that these two types of spaces have is that the product of Hausdorff spaces is Hausdorff and the product of regular spaces is regular. And so because RL is regular and is Hausdorff, then RL squared, this organ-free plane that we saw a few videos ago, is regular and it is Hausdorff. So the question is, well, is it normal? And we will see that no. This will be a good example to see that the product of normal spaces is not necessarily normal, and also that a space can be regular without it being normal. So we'll see this in the next video.